So, students, I hope everybody is fine and everybody is having a nice time. And what's my intuition to talk about in this video is to introduce you with the concept of electron spin. And if we talk about quantum mechanics, it certainly does explain the properties of hydrogen atom. And that too in a very, very straightforward way, in a beautiful way, in an accurate way. But at the same time, it cannot approach a complete description. It cannot give us the complete description of the atom or any other thing without taking into account the electron spin. So the point is that what I'm trying to talk about here is that making use of quantum mechanics to the problem of hydrogen atom, it does give us a satisfactory, comprehensive description of hydrogen atom, but it's not exactly complete. They happen to have certain lacunas and uh, and uh, uh, and the theory of an atom that was developed in the previous lectures, in the previous videos, they could not account for a number of well-defined experimental observations. And what are those experimental observations that I'm trying to talk about? Is that one is the fact that many spectral lines, what we see, we have a spectral line. Okay, it consists of two separate lines, and that too, these lines are very close to each other. If I have to take an example of the fine structure that we used to find experimentally, the fine structure for the line of Balmer series, and what we see, the Balmer series for hydrogen atom, and this thing happens to come by virtue of a transition between n equals 3 to n equals 2. So you have a transition from n equal to 3 to n equal to 2 to level in the hydrogen atom. And what is the theoretical prediction here is of a single line. So when you have a transition, you have a single line. And the wavelength of this single line is 6,563 angstrom. But in reality, what we see is there are two closely spaced lines. This is not the reality of it. We see two closely spaced lines, and maybe this separation is of the order of 1.4 angstrom between the lines that we see. And no doubt this effect is very small, but it's a failure. It's a failure of quantum mechanics to predict a single line, because what we observe is that this single line is made of two closely packed lines. And there was another failure. I would like to go in detail with that failure to have some idea about that failure. Is that the quantum mechanical theory of atom, it occurs in Zeeman effect. We have talked about Zeeman effect, and if we rightly remember what we observed there, we had three lines. Okay, so there we saw that the spectral lines of an atom in magnetic field, we apply the magnetic field, and they split. The spectral lines split with nu, then nu plus d nu, and nu minus d nu. So we have three components there, and this is what's called as normal Zeeman effect. And if to be focused, indeed, if we observe what we observe in the spectra of few elements under certain circumstances, more often this is not the case. We can have more than three lines. We can have four lines. We can have five lines. We can have six lines. Or there can be more components may appear, even when three components are present there. Spacing may not exactly agree, even if we have the three lines. What we predict theoretically, the spacing between the energies, that may not agree. And what we have is what we call this is as anomalous. We call it as anomalous Zeeman effect. And these were the lacunas of the quantum mechanical approach, where we discussed hydrogen atom and tried to see the consequences, tried to explain some of the phenomena that are involved in hydrogen atom. Not all the processes could be explained purely, and the concept basically started from in order to account for this what I said about the fine structure. Okay, you have two lines for one line, and in case of Zeeman effect, you have many lines, and what was proposed. What was proposed by two great scientists of that time, probably in the year 1925. It was Gauss-Smith and Hellenbach, and what they proposed, Gauss-Smith and Hellenbach, and what they proposed that every electron. Suppose this is an electron, I'm drawing it for the sake of argument, has an intrinsic angular momentum. It has its own angular momentum, and this angular momentum is called as spin, and whose magnitude is same for all the electrons. And this intrinsic angular momentum is associated with the magnetic moment of this electron. If you rightly remember, we had a relation between orbital quantum number and orbital angular momentum as L times L plus 1, then it cross. So what they proposed is purely in classical sense. They proposed a spin intrinsic to the electron. All electrons have the same magnitude of spin, and this spin has a correlation. It has a correlation with magnetic moment in order to explain the anomalous Zeeman effect. So this is our anomalous Zeeman effect. If the magnetic field that's applied is weak enough, what we see many more lines in addition to the lines that were observed in normal Zeeman effect. And this Zeeman effect is called anomalous. It's called anomalous Zeeman effect. And Gauss-Smith and Hellenbach, what they did, they came up with an idea of the spin that's associated with the electron. And to move on, what Gauss-Smith what was in their mind was purely classical in nature. It was the classical picture of an electron. It was an electron with an angular momentum having some axis and spinning like that like that of a planet spinning on its axis with respect to the sun. And this rotation involves angular momentum. And because the electron is negatively charged, it has a magnetic moment, mu s. And this magnetic moment is opposite. It is opposite to the direction of its angular momentum. It's opposite to its direction of angular momentum s, which is a vector. Okay, and this magnetic moment is also a vector. So we understand these basic physical quantities. Now, the notion of electron spin, it certainly proved very effective. It proved to be successful in explaining not only the fine structure. It did not explain us the fine structure that I talked about, a single line with two lines. It could also explain us the anomalous Zeeman effect, and even other varieties of atomic effects as well. Now, the picture of electron as a spinning charged sphere uh, is open to serious objections, because in quantum mechanics we don't have trajectories, and we don't have a geometrical spin motion of an electron. For one thing, observations of scattering of electrons by other electrons. If we have electron and we will scatter this electron, and using the scattering experiments, we could calculate the size of this electron, and that's nearly 10 to the power of minus 16 to 10 to the power of nearly 10 to the power of minus 16 meters across, and quite possibly is a point particle, that from scattering point of view, it's a point particle. It's a point particle, right? So small an object, if we think closely, uh, this object has to rotate with an equatorial velocity many times greater than that of speed of light. If we take it classically, if we take the rotation, spin angular spin motion of this electron, by virtue of its size, diameter, and to be a particle and to have a spin in classical sense, it must have the rotational velocity many-fold greater than c. So now the failure of the model taken from everyday life does not it does not invalidate the idea of the electron spin. We have already found plenty of ideas in relativity and quantum physics that are mandated by experiment, although at odd with classical concepts. And what happened in 1929? In 1929, the fundamental nature of electron spin, it was confirmed by Paul Dirac. So Paul Dirac, it was in the year 1929. And what he did, he found that there is a fundamental property associated with electron, and that fundamental property is the spin of this electron, using relativistic quantum mechanics. What he used is the relativistic quantum mechanics. And he found that the particle with the mass and the charge of electron must have some angular momentum. And if it has angular momentum, it must have magnetic momentum, what was proposed by Gaudsmith and Hellenbach. So the quantum number that we have for this spin is S, and it describes the spin angular momentum. It describes this spin angular momentum of the electron. And the only value this S can have is 1 by 2. And which follows from both. It follows from Dirac's theory, and it follows from spectral analysis of these atoms. So the value for S should be 1 by 2. And the magnitude of S, if we talk about the overall magnitude of S, of the angular momentum due to the electron spin, it's the replica of orbital angular momentum under root of S into S plus 1 times h cross. Now, since S can have a value equal to 1 by 2, so this S will be under root of 1 by 2 times 1 by 2 plus 1 times h cross. So S will come out to be under root of 3 by 2 h cross. This is the same formula that we have had for solving hydrogen atom, and using this condition to satisfy the equation. And there, what we have had was L equals under root of L into L plus 1 h cross. And so to say is that what we have automatically space quantization of electron spin. Now, electron has spin and its value is 1 by 2. And what we have quantization of space quantization of electron spin. And this space quantization is space quantization. This space quantization is described by the spin magnetic quantum number. Spin magnetic quantum number. So to say, if we go back to the concept of angular momentum, the angular momentum can have the values 2L plus 1. What we used to say is from minus L via 0 to plus L. Right? In the same way, we have we have the values for spin as 2s plus 1. So in orbital angular momentum, we have this much of orientations, quantizations of orbital angular momentum in space. And in case of spin, we have 2s plus 1, which is simply equal to 2 times 1 by 2 plus 1, that's equal to 2. So we have two orientations for the spin of an electron, and one orientation is ms equals plus half what is proposed as up, and the other is minus half that is proposed as down. So the components of this magnetic field, if we have to draw the components of this spin, this space quantization of spin, if we assume that this is the z direction of spin, say sz, what we have, suppose this is the origin, and here we have plus h cross by 2, and here we have minus h cross by 2, and we will have a vector, and we will have another vector, and this will represent ms equal to plus half, and this will represent ms equal to minus half, and this should be plus, so corresponding to this, and this will be corresponding to this. So if we have to write down this z component of spin angular momentum, suppose that is sz, that will be ms times h cross. That should be the case. Now ms is what? It is plus minus half h cross. So If we rightly remember when we talked about the orbital quantum number, and when we discussed Zeeman effect, we introduced there a symbol G, and this G refers to gyromagnetic ratio. The gyromagnetic ratio of the electron that we had, electron's orbital motion, and it was equal to minus E by 2m. Now, the gyromagnetic ratio characteristic of electron's spin is almost exactly twice that of the characteristic of electron's orbital motion. Now, taking this ratio as equal to 2, the spin magnetic moment of an electron is related to its spin angular momentum s by, so taking a spin magnetic moment equal to it, what the factor comes is 2 times minus e by 2m times s. So this 2 and 2 goes, so we have mu s equal to minus e by m times s. And we better understand this mu s is the magnetic spin magnetic moment of electron, E is the charge of electron, m is the mass of the electron, and spin is s is the spin angular momentum of electron. Now, the possible component of this mu s along any axis, say for the sake of argument taking the z axis, what will be its possible value? They are limited. These values are limited. So mu sz, let us assume that is mu sz, that is plus minus eh cross by 2m. And what is this? This whole thing is the Bohr magneton, and mu sz is plus minus mu b. Okay, and this is what the introduction of electron that was proposed by Goudsmit and Hellenbeck, and this certainly solved a range of problems that were arising in explaining various things. The very first thing was the fine structure. The second important thing was anomalous Zeeman effect. And so many other things could be resolved by including the spin angular momentum of electron.